to talk today about a question that sounds very abstract and philosophical, but I think is close to all of our hearts on the stage. And I think it's more than philosophical. It's somehow probing our deepest thinking, which is mathematics invented or discovered? And when we were first talking about this, so many people presumed discovered would be the thing we would all say, and I had to actually convey that many mathematicians will say invented. Many mathematicians will say invented. And so I think this is a real interesting conversation to be had, and let's talk about math. Max, I would love in the beginning to pose to you the question, is mathematics invented or discovered? And then we'll spend the rest of the conversation kind of picking it apart.
Well, we'll have a lot of fascinating discussion tonight, I think, about precisely what it is that we're going to argue about, whether it's invented or discovered, for starters.
Yeah.
So you'll see there, I think we agree quite a bit here. And then
well, we will establish that we all agree on math.
There's a broad spectrum of opinion on this question, obviously, and I think Janna has done a great job at picking two people on kind of the opposite extremes of the spectrum to make it maximally fun for you and for us.
That's right.
And Rafael, is mathematics invented or discovered?
Definitely invented. But there's a but.
We will see.
There's room for discoveries within what we invent.
And I did mean to give a trigger warning. This presentation contains images of math. And that could induce a math anxiety episode. But I do want to add the caveat that it's okay if you don't understand the mathematics. It's okay if you only appreciate the visual beauty. What we're talking about is something that we believe to be fundamental, at the very least, to human beings, if not to the universe. So we're all in this together. I wanted to begin with this famous quote from Wigner, "The unreasonable effectiveness of mathematics." Rafael, what does this famous quote mean to you?
Well, that's a great quote by a physicist. And that means that physicists look at the world in a certain way. And a lot of the history of mathematics have been shaped to serve the purpose in physics. And physics is a domain, I mean, of course, much more complicated today, but let's say since Galileo, you would observe, let's say, falling objects and planets moving and so on and so forth, and mathematics has been developed using human intelligence and human cognition and the human brain, human language, human societal practices, and writing notations to serve the purpose of making sense of these things. But the kinds of phenomena has been mainly physics, let's say, drawn by that. But if you look at other aspects of nature, biology, human emotions, artistic creation, and so on and so forth, then the mathematics starts to break down. So there are quotes like that of the unreasonable ineffectiveness of mathematics in domains that are other than, let's say, than physics. But it's a great quote by a great scientist.
So you think that Wigner was a mathematics is discovered person, and you're doubting that that's right. But I do want to ask Max, because I can tell already, because I know you so well. Tell me what you have going on in there.
So I agree that if you're a medical student, for example, or if you're doing sociology, maybe there's not so much math in it. But as a card-carrying physicist, I have to say, no offense to the doctors in here, but you are all a bunch of quarks and electrons moving around each other in a certain pattern, which is physics.
He didn't say quacks, he said quarks. I just want to clarify.
Exactly. And so ultimately, this is all physics. And I think you are some of the coolest arrangements of quarks in our known universe, but that doesn't change the fact that it is ultimately physics. And when I said that I think math is discovered, and that I'm way out on the edge of this spectrum, I would go even further and say not only are we discovering something that's out there, that's fundamental, but it's the most fundamental thing that there is. Because as we'll come back to later, I think the reason why physicists like Wigner have been so wowed by how effective math is at describing physics is because when you really look closely at physics, it's all entirely mathematical. You know. And this might sound just really shocking, because when you look at Janna here, right? I mean, what's so mathematical about her? Apart from the fact that she's good at it. You know, what are the properties of Janna? Well, brunette, friendly, smart. They don't sound like math properties, do they? But if we look at her again through a physics lens, she is about 10 to the power 28 quarks and electrons in a certain pattern. And what are the properties of an electron, you might ask? Well, I'll tell you. -1, 1/2, 1, and so on. And we physicists have made up fancy pants names for these properties. We call them the electric charge, the spin, the lepton number, and so on. But the names are just invented. That's the language we use to talk about them. But they are just numbers. And in fact, the only difference we physicists have ever discovered between an electron and an up quark and a down quark and a photon, which is a particle of light, are what numbers their properties are. So if you start, and then what about the space that all of Janna's particles are in? What are the properties of space? Well, 3, for example. That's the largest number of fingers you can hold that are all perpendicular to each other. Again, we made up a name for that. Mathematicians call it the dimensionality of space, but that was invented. We call it something else in Swedish and in Spanish. The property is 3. And after Einstein and others studied space more carefully, they discovered it had some other properties also that we call curvature and topology, which you can also read about in math books because they're math properties. So if all the properties of the particles that make us all up, and also the stage that the particles are moving in, the space, are also all mathematical, it starts to seem a little bit less crazy, this idea that our universe maybe is all mathematical, and that the reason why physicists have found mathematics so convenient, so useful, so unreasonably useful, is because that is the basic properties that it has.
So it's not to break my unbiased facade, but it's fascinating what you say when you list the properties of an electron, because there's not an electron in the universe that deviates from exactly those numbers exactly, right? And I think that's a very subtle aspect of this conversation that's very intriguing. Now, Rafael, I put up on this board here Stephen Strogatz. He's a mathematician from Cornell. He just happened to give me this picture of a board in a class he was teaching. And we don't have to dissect this board, but it was so beautiful I could read it from beginning to end. And now, Rafael, you've thought a lot about the difference between thinking about mathematics in the world and thinking about notation, names, language about mathematics.
That's
now,
right.
This is clearly human, and this is clearly a specific group of humans, and if we were wiped out, it would look different.
That's right, but I want to go back to the previous thing,
Okay,
because I'm not done with that.
Yeah.
So I'm here sitting between two physicists, so...
My condolences.
Exactly. Because in that quote, and I'm going to get back to that one, but in that quote, there is the idea there is a mathematics. And when we go to school, we learn a mathematics and certain rules, and and then so we get the general picture that there's one single, beautiful, crystal clear edifice called mathematics. A lot of the physicists and people who use mathematics to do science would grab a part of that building. Let's say, for example, what's called classic mathematics from, let's say, analytic geometry on, the 17th century on kind of mathematics, and then would apply to certain phenomena. And then mathematics would be seen as that. And that's what is taught today in STEM classes. The curriculum is all formed by that kind of classic mathematics. But if you really go in depth into practices of mathematics, there's many mathematics with different axiomatic systems. So axioms are these basic fundamental building blocks on which fields of mathematics are created. So Euclid was the first one who put this together, like 300 BCE, in which it's okay, you know, we're going to all this knowledge about geometry, but we're going to put it together in, you know, 4 basic beliefs, things that we take for granted, like, for example, the parts are bigger, and the relative relation between parts and whole, or 5 postulates for geometry, that you can only draw 1 line through 2 points and that kind of thing, and then build the entire geometry. But we know now, from the 19th century, there are different kinds of non-Euclidean geometries with different axiomatic systems. And so it goes for set theory, for number system, infinities, different forms of infinity. So there's no one mathematics, there's many different types. There's calculus, as you teach it in, let's say, college, but there's also forms of calculus that are non-standard, that take other elements in order to build that. So what I'm trying to say here relative to that quote is that it would be interesting to know what mathematics are we talking about, because when you look at that, you start to see the human hand in making all these sense-making possible.
Max.
Yeah, very important point being made here by Rafael. And what you casually refer to as different mathematics is what, of course, mathematicians usually refer to as different mathematical structures. And I think it's worth talking a little bit more about what a mathematical structure is. And Janna, you have a bunch of pictures of them even here.
Yeah,
Like,
do you want to go? Do you want to go look at this mathematical
Well,
Sorry,
structure?
I took you off your
Like-
your
No,
track there.
yeah,
with your thing.
here's a mathematical
Yeah.
structure
We're
you
here
know
for
and love,
fun.
the triangle.
Do
And
you want it to become a circle?
Here's another one, here's another one. And so some mathematical structures are geometric shapes in 2 dimensions, like these polygons. Other mathematical structures are different kinds of numbers that Rafael mentioned. You have the whole numbers, 1, 2, 3, 4, 5. If you put then you have the integers where they can go negative. That's a different structure. Then you have the real numbers, the ones with all the decimals. Then you have the complex numbers, et cetera, et cetera. And then there are different kinds of spaces. We heard here how there's the Euclidean space, the one that Euclid actually thought we lived in, where 2 parallel lines just go on forever and never cross. And then later on, Lobachevsky and Bolyai discovered that actually there are other kinds of spaces too. And now it became a physics question. Well, what kind of space is this then? And the answer turned out to be neither. Our space is not like Euclid, but also not like Lobachevsky's space. It's curved in a more complicated way. So there are many different kinds of mathematical structures. And mathematicians themselves, of course, love to argue about how to define mathematics, which is why you should feel if you don't fully understand exactly how to think about this, don't worry, mathematicians, this is not the resolved issue. But the key point is, a lot of my mathematician friends today will define mathematics simply as the study of mathematical structures. Some mathematicians study this structure, some study pseudo-Riemannian manifolds, some study Lie algebras. There's a professor, David Vaughan at MIT, who spent 10 years studying one and the same mathematical structure. It's called E8, and he has a picture of it on his wall. He has like a close personal bond with it. Like some people have a picture of their dog. He has E8 there, and if so now the question becomes: if you think that physics, this world is mathematical, then which structure is it that we live in? And Euclid thought that we lived actually in this Euclidean space. Well, that was wrong, turned out. And then Einstein came along and said, "Oh, I got this. It's a different kind of space called the pseudo-Riemannian manifold with tensor fields." And then quantum mechanics came and showed that was also wrong, and said, "No, we live in a Hilbert space. Problem solved," which is a weird kind of infinite dimensional space. And then gradually it became clear that quantum mechanics, the study of the small with its Hilbert space, and Einstein's curved space covering the big, they didn't get along. They were inconsistent. And we're still, if you watch the Big Bang Theory, arguing about whether it's string theory or loop quantum gravity or how exactly to unify this. So we haven't figured out yet which mathematical object is a candidate for being the one we live in. But what I'm guessing is that at the end of the day, what we live in is some mathematical structure, some really cool one, which is complex enough that it can support this.
I only want to, and I don't think you'll disagree with this, say that it's not that they're flat out wrong, the Euclid, Einstein, it's that they have limited domain of validity. So it works real well for a while. So let's do another example of something that might not be exactly right. So let's do a simple math experiment. Okay, imagine we begin with this triangle, and now we're going to keep adding sides. And the question is, well, it's not really a question. We're going to get to something with an infinite number of sides that we call a circle. Now, everybody in this room can do this experiment in their mind. And I once had a Platonist say this to me. Here's an experiment. Imagine a circle. Now, there is no such thing as a circle in reality. Do you, Max, think that there's a circle in reality?
By reality, do you mean
In
the
the
particular universe that we're in?
Okay, I deserved that. I totally deserved that. So let me rephrase. Do you think that there is any physical object that is a perfect circle? Physical, material object that is a perfect circle?
I think in this universe that we're in now, I think no. But
Some other universe.
So let's...
That's a really, really deep question, right? Because this is the most radical part
That's an easy.
of what I believe. If it is true that we live in a mathematical object, a mathematical structure, and if it's also true that there are many other mathematical structures too, you know, that's kind of unfair. Why should some mathematical structures have this extra privilege that they can have, that they exist in some sort of physical sense, and others don't? If we already agreed that the only properties that they have are the mathematical properties. So I actually argue in my book, right, that all the other ones exist in just the same way. It's just that, for example, the circle is just way too simple. There's no consciousness in the circle. There's nobody there experiencing anything and having psychons. So that doesn't mean it doesn't exist. But it's kind of stillborn.
Object? I mean, Rafael, can you think of a physical object that's a perfect circle? Physical material
No,
object.
because I can actually bring your experiment to something much simpler. The simplest entity in Euclidean geometry, where the circle is supposed to be defined, is the Euclidean point. So that line that you see there has a width, but the circle in itself should not have any width, right? So what is a Euclidean point? Well, Euclid defined that as an entity that has only one property: location. Nothing else. No color, no texture, no extension, nothing. Just location. Now, what microscope in the world would be able to see a Euclidean point? None. Because it's imagined. That's the whole point.
Do you think there's any physical material object that's just a point?
But wait, a Euclidean point we're talking about. A Euclidean point has only location as a property. So as such, you cannot observe it directly with it in an objective sense, because nothing has only location as a property. So you would have other things like mass and you know, whatever, velocity and things, but not location only. Now, if you build the whole edifice of geometry, Euclidean geometry based on that, now you have 2 points, both imagined and idealized to have just one property. So we see location as thinking, well, Max is sitting here, you're sitting there, I have my glass here. These are objects in space, but I can idealize them, which is a human cognitive activity, idealize and cognize, use the cognitive mechanisms to idealize to the point that I only see one point here. And then I can calculate the distance between the center here and Max's glass and so on. Now, the thing is that this is all human sense-making. That's the whole point. Made possible with the human neuroanatomy and human mechanism. So the questions that you ask about the circle can be asked about a single Euclidean point. And in that sense, there's nothing in the universe that is really existing in the objective sense, because it's imagined by humans. And the question is, it's not just hallucinated by humans, it's created conceptually by humans, not just, as Max saying, a name for a point or a number. The concept is a creation, and then there's an entire network of how things are created, which are not purely, let's say, random. They follow ways in which humans make sense of reality, of things and phenomena and experiences, and then you can study that empirically through language, history, archaeology, neuroscience, and others, because it becomes an empirical question of how is it that humans crystallize and understand abstract objects and make up concepts in a systematic way.
Max, please.
Yeah, so here there's one thing I agree with and one thing I disagree with. What I strongly agree with is the whole business about Euclidean points is not describing the actual physical world that we are in tonight, you know, and I feel kind of guilty when I teach physics courses at MIT that I'm actually kind of like lying the whole time when I'm saying, hey, no, the distance, let's call the distance between here and here x, which is a real number with infinitely many decimal places, even though I know that's BS, because not only can we never measure anything to infinite precision, but we have very good reason to think that it doesn't even make sense to talk about distances shorter than 10 to the power minus 34 meters because of quantum stuff. And when we do derivatives and integrals and calculus things, we're constantly flirting with the infinitely small, which which we're pretty sure doesn't exist, and also sometimes with the infinitely big, which we have no real evidence exists. So these are all. So here I completely agree. We have a shared humility, you and I, that we don't understand exactly what this physical universe is like. On the other hand, where I think we differ is where we conclude from this. I think you conclude from this that there's really no evidence that the correct description of our universe, or the correct actual nature of it, is mathematical. And my guess is the opposite. If you live in some, because what we've seen again and again in math is that you can take some quite complicated mathematical object and often find that it's really well approximated by something much simpler. Like, for example, if you take a polygon, which is not the pentagon, but which has a googolplex corners, so that's one with a googol zeros after it, where Google is one with 100 zeros. That's very complicated to keep track of, but it's going to look almost exactly like a circle. So you can approximate it by something simpler. That's the real reason I lie to my MIT students also, and say, let's just take this air here and treat it as a perfect fluid where it has a density and a pressure at every point. But you know that's not true, because there's just a bunch of atoms bouncing around, and if you look really close, either you're inside an atom or you're not. But yet, so what I think is happening is all the incorrect physics theories we've come up with so far, Newton's theory, Einstein's theory, etc., are really not. We should think of them as math approximating the more complicated math, which is the actual math that we live in. And it's quite remarkable, I think, how much better we've done. You know, when you mentioned Galileo in the beginning, he has this famous quote from about 400 years ago when he says that our universe is a grand book written in math. What evidence did he base that on? Well, the only thing Galileo could do with his math in the universe was figure out how the motion of things. If he threw a grape and a hazelnut, he could predict that they would both move in this mathematical shape he called a parabola, y = x squared, mathematical. But he had no idea why the grape was green and the hazelnut was brown, why the grape was soft, the hazelnut was hard. So if he was right, that it was ultimately all math, then Galileo could have predicted that future generations would be able to describe these more things about the grape and the hazelnut that he couldn't. And that's exactly what happened. Maxwell came along with Maxwell's equations, which obviously are mathematical, and they describe light and colors and things like this. And then quantum mechanics came along, the Schrödinger equation and so on, and described why the hazelnut is hard and the grape is soft. And today, and here I think you'll agree with me that we've almost gone full circle from physics being able to describe almost nothing with math except motions to being able to describe pretty much everything around us except consciousness and intelligence, and even with intelligence, our AI researchers
and
are
immune
making some
systems
progress.
and endocrinological system and the neuroscience of synaptic clefts. And
So there's lots left, but I think you'll agree that we're no longer in the situation where most of it is just we have no clue, right? there are these holdouts, and I don't think we should dismiss them. Consciousness, for example, the subjective experience. But this, I think, supports. This is how we do science. You predict something, and then you wait for more evidence. Since Galileo made this claim, I think there's been ever more examples of unreasonable effectiveness of math. Even after Wigner said this stuff, we were able to describe our expanding universe mathematically, which you have done a lot of research on, right?
Mm-hmm.
I think
So
the
keep
main,
on coming.
sorry, I think the main difference is actually, now I'm understanding a little better, is we have different goals. And then from the findings of the practices in our own sciences, we make different conclusions relative to the question of invention and discovery. So in your case, you're trying to understand the structure of the universe. And out of all that, so all the examples and all the arguments are with respect to that, right?
Yeah.
Good. Well, I'm not doing that. So in my work, what I'm trying to understand is human abstraction. How is it that this animal that has been around for about 200,000 years, maybe a little more, depending on who you ask and what the evidence is, but it's, one type of vertebrate that belongs to evolution and parts of, with other species and in this ecosystem. But how is it that this particular species, Homo sapiens, came up with language that has a grammar, that has, cultural practices and cumulative of knowledge and so on? So from that perspective, how is it that among all these techniques for making sense, and not techniques, but forms of, religion, poetry, art, practices that we try to make sense of our experience of what are we doing here, what happens after we die, and so on. Well, mathematics is one of them.
Mm-hmm.
It just excels at certain things. It's a beautiful edifice. I love it. But it's just part of this process of sense making that has a history and a path.
Yeah.
So from these two scientific endeavors, I would say, we make conclusions about these questions, and I think that's where we differ. So with respect to that, for example, making, we all go to school, at least in this part of the world, and we're taught certain things about mathematics. But for example, one rule you learn is that when you multiply two negative numbers, the result is positive. How many of you were taught that rule? Some hands, okay.
I don't know if that's good or bad for our education system.
Okay,
seriously.
I don't know about that. But now, how many of you were taught why is that the case? Fewer hands, okay. Right, so if you look at the curriculum, you really see that most of the time you're taught the rule, but you're not explain why the rule is necessary. I could make another one, like 0 factorial equals 1. So factorial is that operation, right? When you have, let's say, 3 factorial is 3 times 2 times 1. 5 factorial, 5 times 4 times 3 times 2 times 1. 2 factorial, 2 times 1. 0 factorial, what the heck is that? Because when you multiply by 0, the result is 0. So why would where do you place that even to begin with in the definition? Well, it turns out that 0 factorial equals 1. So then the question is, where in the universe there's a sign that that's the case? And the answer is, there's no sign in the universe because, Max will say something, because it's a good convention that solves many problems in other parts of mathematics that it's innocuous. It doesn't create contradiction. So then it's adopted. Many examples like that. I don't want to mention more complicated math, but you have many in math in which you can really see the human hand trying to fix the thing and making sense of this apparatus and extending it and making it apply to phenomena.
Yeah, so I have a question for you, actually.
Oh, I thought you would say where in the universe you find 0 factorial
I'll come
equals
back
1.
in about 20 minutes.
We could talk,
Okay,
talk about the gamma
what's the
function
question?
later. Over drinks. But the question is, so first of all, I have to say, even though I have and will be giving you a hard time about certain things perhaps we disagree, I have to say I'm a huge fan of your research that you do, and I think it's really, really awesome. The only place where we differ is how we interpret what that means for whether mathematics is invented or discovered, and whether our universe sort of is mathematical or not. So here's my question for you. In general, if you want to know whether something is true or false, right, it's very interesting to ask, you know, when you do science, you're like, okay, I'm going to measure this thing and see if it's this way or that way. And if it's this way, I predict to see this. If it's that way, I predict to see something else. That's how you look at the measurement and figure out whether it's which of the two ideas it supports. So let's for a moment just assume, to suspend your disbelief, and let's just assume that our world that we live in is completely mathematical. And let's pick for fun.
Wait, I need a sip of water to assume that.
Maybe something stronger. You're welcome to stop assuming in a minute.
Okay.
To make it even simpler, let's suppose we live in a computer simulation. You've probably had a SciCon on that, right?
Not yet.
Okay, at some point there will
This might be it.
there will be a SciCon where we live in the matrix.
Okay.
Or people argue about it. But let's suppose for a moment we do. So we are actually just like characters in some super fancy computer game that someone has written. But it's such a sophisticated simulation that even though it is, of course, completely mathematical, that the computer chip is just chugging away, multiplying numbers and running the simulation, it feels to us, obviously, exactly the same way it did a minute ago. We experience colors and emotions and have these thoughts, etc. That's just the way these entities in the simulation experience the world. So suppose for a moment that's true. Would you still say then that, how would your research have come up with, what results would your research that you're doing in the Amazon and so on find? Would it find exactly the same result, that these simulated indigenous people in the Amazon would speak the same language, and would you still argue that our universe is not mathematical in this case, even though it by assumption was?
Well, what you describe is called a thought experiment,
yes,
right?
Exactly.
Gedankenexperiment.
Gedankenexperiment, exactly. Like
And those
Einstein
are
would say.
cheap because you don't need money.
They're the best. We want to respect Janna's budget here.
sorry,
you know.
sorry.
Her donors are generous, but
I
up
didn't
to a
mean the
limit.
word cheap as an insult, but I meant like, you know, it's good because pushes for boundaries of conceptualization
Yeah.
and hypothesis.
Aren't all
I agree.
mathematical experiments thought experiments?
What's that?
Aren't all mathematical experiments thought experiments?
Bazinga.
Well, you know, that's another topic we can jump in. But the point is that when you have a thought experiment, usually there are a bunch of assumptions, and you mentioned very clearly which one was here. So the problem is, do you really buy the assumption? And what are the basis for buying the assumption? So for example, in neuroscience, I remember in discussions 15 years ago about consciousness, some philosophers saying, oh, let's imagine the nervous system is just one big computer. So now, you know, you have a bunch of neurons, but now you replace one neuron with a chip. Okay, done with that, then you replace another neuron with another chip. Done with that, you do more. At some point, the entire nervous system is just a bunch of chips. Then now you ask a question. But then it's like, well, you can't do that. It's like, that doesn't make any sense. It's like, let's assume that tomorrow already occurred and yesterday has not occurred. It's like, okay, well, where are we going with that? So the bunch of assumptions, I think, determines what you're going, the conclusions you're going to make. So when you mention the Amazon, for example, to me it's more like, we assume that numbers exist for all humans. But when you do the empirical work, you realize that millions of humans don't have in their culture or languages numbers for quantities, exact quantification that is, beyond 5 or 4 or 6 depending on the language. The entire Australian continent, which was populated 50,000 years ago, 50,000, okay? Just to give you the impression of how long that is. The language we're speaking right now is English. English is an Indo-European language. Indo-European languages that include Icelandic and include, you know, Latin-based Romance and Farsi in Iran and so on, they had a common ancestor about 7,000 years ago. That's 7 times less than the time that Australia is being populated. In Australia, there's hundreds of languages. In none of them, until the arrival of the Brits, there were exact quantification beyond 4 or 5.
But I think I have to apologize for not
But there
explaining
were
my
many,
question better.
many words for natural quantification. Few,
Uh-huh.
several, many, and so on. And so it turns out that humans are pretty good at surviving in an island for 50,000 years, raising kids, migrating, finding food, protection, etc., from animals and
Right.
other environments, without the exact
But
quantification.
like, if
are
you
we
take
sure
so-
that they're
I
not, it's not just that they don't have the words for it in the same traditional way that we name things,
Mhm.
but they have a concept for it that's translated differently?
Well, the thing is that, we may have a word for certain things. For example, what is the name for a regular polygon of 12 sides? I mean, maybe you can learn that name, but
Is that the icosahedron? I get them all confused.
Oh, that's when you go to 3D.
anyway, the point is that when you get the concept of
definitely.
regular polygon, then you have the notion of adding one more side and regular, etc., then you can sort of come up with a concept without having the name.
Without having the name.
But when you don't have, let's say, a concept of 8 as being different from 7, when you have things that you would say how many are here and how many are here, it's just like a few, a
Several.
bunch.
Right.
There's let's say I can see way more people sitting than, let's say, here than in the back, but I don't know how
Isn't
many.
that just
Total
because it
sense.
doesn't matter the exact number?
Well,
Exactly.
that
Some
makes-
survival
exactly.
Exactly. So
Exactly.
the idea here is like, let's say you take a good cook, and look at what he's doing when he's cooking. He's not measuring like every detail of how many crystals of sugars or what. It's just like taste, add some, maybe a little bit more here, more fire, less fire, too humid, whatever. So when experts do what they do, they don't go into all these details. So in a certain way, if humans have been experts at raising kids and finding patterns in the environment for doing migrations and so on, then apparently, and this is now empirical fact, for
Yeah.
50,000 years, numbers were not needed.
Yeah.
And now, it's not the only region
So-
in the world, by the way. The Amazon you mentioned is the same. You
right,
have
but to just
hundreds
come
of
back
languages,
to
the
the
same
question
property.
I asked here, I realize I did a poor job really explaining it well. Because what you're saying here, I agree with. Whether we invent things when they're useful for us, right? If it's enough to talk about whether it's 1, 2, 3, or more, because counting isn't so important for higher numbers, it's not useful to invent them. Whereas raise your hand if you work in finance. No, for you, it's really useful to know the difference between a million and a billion. And if you
That's a
look
pretty
now,
big mistake.
raise your hand if you've ever played Pac-Man. So you remember how there, in addition to the Pac-Man that you control, there are these little monsters that are controlling themselves. The computer is controlling them. So that's a much simpler simulation than the one we were talking about earlier, the Pac-Man game. But you'll agree it's completely mathematical because you can look at the program and it's all do this, multiply these numbers. Those monsters in Pac-Man, they don't have the concept of number. I don't even think they're conscious at all.
That's right.
So
I'm
I
glad-
don't, that's
You
why I
don't
don't feel
think.
so sorry about eating them when I'm Pac-Man.
I'm glad to hear that.
Yeah, and they don't need to. It's sufficient. It's not. There's not any need for them to be able to know how to count or talk or anything to do what they're supposed to do in the Pac-Man game. And similarly, if you're a chipmunk, being able to factor prime numbers is probably not very useful to you. And they don't need to. It's sufficient. It's not. There's not any need for them to be able to know how to count or talk or anything to do what they're supposed to do in the Pac-Man game. And similarly, if you're a chipmunk, being able to factor prime numbers is probably not very useful to you. So I don't think that's an argument for the underlying reality not being mathematical, that some biological entities didn't find it useful to develop math. Conversely, for us, we have invented a lot of things that were useful, some of which were not math also, like English, where we take the experiences that many other animals also have of how things look and how they smell, and then etc. And then we invent symbols that let us abstractly represent them and communicate them with each other this is what we're doing now when we speak English. And in some way, mathematics as a language is just the most abstract form of this endeavor, where it's where you have, it's just very rigorous, much more rigorous than English with all its funny exceptions and stuff like this. So coming back to the question to you again, I'm wondering if this whole world were actually simulated, not Pac-Man now, but these laws of physics. And you went and the simulated you went and interviewed some of these simulated people and studied their language, which by assumption is exactly the language that they're studying in this world, right? Wouldn't you publish the same research papers and saying, well, this many % of the Aborigines in Australia didn't invent numbers beyond 5? And since that is a world which by assumption is mathematical, because it's a simulation, doesn't that mean that we cannot conclude from your research that the world isn't mathematical?
Right. So the problem, I want to be clear here, when I say that the Aboriginal Australians did not have language, well, it's an empirical fact to begin with, and same happens in other parts in the world in Amazonia. But I'm not saying that they're stupid or primitive. It's just they did not care about exact quantification.
Because it wasn't useful.
When you look at their languages, they're so amazingly sophisticated, marking all kinds of things that English doesn't have. You know, they have amazingly sophisticated kinship systems for tracking, you know, genders of various generations and you know, intermarriage and clans and names for each of them and so on. So when you compare that to English, you say, oh, English is like so dull because you only have brother-in-law and that's it. That's the most sophisticated concept you can get. And it doesn't even say whether it's the sister of a person you married or the other way around. So
in Swedish, my mother's mother is different from my father's mother.
Well, there you go.
More than 5.
Yeah, that's right.
Okay, I've totally indulged you guys. I've been completely off the hook. I mean, anyone who comes to SciCon all the time is always like, yeah, you handle those guys. So I love this, and we're going to do more of this, but I do want to have a thought about Plato, which is part of where this idea of the Platonic ideal existence of mathematics began. Apparently this quote...
Is that more interesting than what we're talking about?
No, I'm so sorry. Carry on. No, you're going to be able to bring it back in. So he says, let no one ignorant of geometry enter here, right? This is allegedly written above the academy. So let's talk for a second, before we go back to this, about why the idea of a Platonic reality even began. For instance, the very existence of the Platonic forms. And sometimes people will say that Plato discovered these geometric forms.
And that's my favorite, the lower left.
Which one? The lower left?
The dodecahedron, yes.
The dodecahedron, why is that your favorite?
Well, 5 was always my favorite number since I was a kid. And it's also the roundest of them. I just like round things.
So why, Max, to you, does this speak about Platonism? Does this speak about an external reality? Can I invent a 6th or a 7th or make up an imagined 8th or 9th?
That's a great
surface?
question. So if you take, for example, the planet Neptune, right? That was very exciting when it was actually discovered. Some of the people were realizing that Uranus wasn't moving quite right, and this Frenchman, Urbain Le Verrier, had this crazy idea that maybe it's because there is some other planet pulling on it with its gravity. And he calculated and he wrote this letter to this German dude, Gall, in Berlin, who had this great telescope and said, on such and such a date, you know, point your telescope to that place in the sky and you're going to find a new planet. He must have thought, geez, these crazy French people. But he must have, obviously he was very curious, so he looked and there was Neptune. So Neptune, the planet Neptune we discovered. Nobody, I think, would claim that we invented Neptune, right? But we invented the name for it. He could have called it Schneptune or Smeptune or Planet Urban or whatever. Right? And it's exactly the same with these Platonic solids, because Plato was just really interested in how many different three-dimensional shapes are there that you can make where all the faces are identical polygons. And for a long time, people only knew about the cube and the octahedron and the tetrahedron, and then they discovered there are these 2 more, and they even kept secret the dodecahedron for a long time because they thought this had like magical powers, and you still find some medieval paintings in art museums where there's like a little dodecahedron down in the corner. So they invented the name dodecahedron. He could have called it the schmodecahedron if he wanted, right? The language we invent. But did he invent the mathematical structure of the dodecahedron? No. If you can't invent a sixth one, there are only 5 that exist. That's it. And
That exist.
And if you define, now we come to this business about what is a mathematical structure. There are many different kinds we talked about. These shapes is one kind, and you can, what mathematicians do when they study them as they prove, they say, oh, this kind of structure, well, how many different kinds exist? What properties do they have? And they can prove, and if you wonder how the proof goes, ask me about it afterwards. I'll explain to you how you prove that there are only 5. So in this sense, we don't invent the Platonic solids themselves. We invent the English language we use to talk about them. We invent names for them. We invent the symbol we use to write the 5 and so on. But the structure itself, the way mathematicians define mathematical structures, it's exactly that which is left when you strip away all the language that we've invented. And just like the planet Neptune, we discover the planet, we discover the dodecahedron, and then we invent language to talk about it.
So, Rafael, why isn't that a discovery of something, even if it's in our minds? Why isn't that a discovery to you? Why is the fact that we can't make a sixth not compelling
that's what
to
I
you?
said at the very beginning. So there's a sense of discovery in which you discover a planet, a star. You discover a new species like, 500 meters under sea level you never saw before. So in that sense, you discover something that you can, objectively refer to. But when you create an entire system based on idealized objects, like we said, all those solids require the Euclidean point because they exist in the Euclidean space. And the simplest entity of Euclidean space is the point, which we said is idealized. So once you invent something...
But why isn't that also in existence? Does it have to be made of matter to be real to you?
Santa Claus exists because we talk about it. It happens in December usually.
I don't think we can all perform the Santa Claus experiment.
What I'm trying to say is that there are all kinds of things that exist because we invented them. But that's a different type of existence from a planet.
But this isn't Santa Claus, we agreed.
Yes.
Nobody in the world could come up with a sixth. Whereas I could come up with a different version than Santa Claus.
Okay, so what happens is, when you invent a particular type of conceptual system, there are entailments of those systems that you're not aware of when you invent them. So it could be that later, 10, 15, 100 years later, you discover certain entailments out of the thing that you invented. It could be, let's say, chess playing. You have the rules, you invent the game, but not every single strategy or move is immediately pristine and clear to every player. So you can discover new ways for doing things. So even in everyday language, one of the most basic mechanisms of human thought for manifested linguistically for holding abstraction is conceptual metaphor, for example. The idea of expressing something in terms of something else. And one thing that we do that all the time for all kinds of things, for money, for numbers that are bigger than others, as if they're really bigger in terms of space. One is the spatialization of time. Most languages around the world conceive temporal notions as if, and refer to, as if they're spatial. So we say looking forward to something, or when I was a little kid, and then you point behind you, as if your childhood is somewhere behind you, and the words forward, meeting, move a meeting forward 3 days, etc., etc. All those properties have entailments. So, for example, if we adopt the conceptualization that we normally do in English, that future is in front of us and past is behind us, as a speaker, then if you have the transitive property, and here's a structure now, that further away in front of you is further away in the future, so it's going to take longer for that event to take place, and so that applies for the past. The immediate past, yesterday would be right here, 15 years ago would be way further back, and you can observe this in behaviors with how people point and gesture, how far they're pointing and so on. Now, If you adopt that invented system, it's totally invented, manifested through language, but also human behavior and motor activity, like gesture production, there are entailments. So if tomorrow is here and the day of tomorrow, after tomorrow is here, then a week from now is going to be further away in front. And that's an entailment of this system. You can say you discovered now that maybe it's in the future. So here, you idealize, you invent the whole thing, and then there's going to be certain entailments that are constrained. They're not just completely hallucinated. They're just very specific constrained entailments that you discover.
Is existence in our mind sufficient, Max? I mean, we have to agree this is not Santa Claus. I can make up many shapes, but I cannot make any more platonic solids than these, period. Nobody in the world can. And it's an experiment that if civilization were wiped out tomorrow, somebody would rediscover, one might suggest. But Max, is an intellectual experiment sufficient? Is this sufficient to convince us the fact that no human being in the world ever before or ever in the future can invent anything but these 5 platonic solids in a Euclidean space?
Well, this is one of the things that mathematicians spend a lot of their time doing, proving that certain things are impossible. Within this structure, with these rules, this is possible and this isn't. So I'm confident that any aliens out there who start taking an interest in beautiful symmetric shapes like this would also conclude that there are 5 of these. They're certainly not going to call them the dodecahedron. Maybe they'll call them the or maybe they don't communicate with sound at all, but it's going to be 5. Now, when you get to very different alien cultures, it all comes down to what's useful to them. There's some things that might be very useful to us because of the particular nature of our planet and our solar system and our bodies that they wouldn't really care about. And then other things that maybe are very useful to them that are not useful to us. But then I think of all of the mathematical structures as forming sort of, if you think of the map of New York City, right? There are probably many of you have never been to certain obscure parts of Yonkers, but everybody has been to Times Square at some point. Right? Who's been to Times Square, right? So similarly, any civilization that starts building technology and trying to make bridges that don't fall down and so on, will at some point find it useful to invent language and they start studying the integers, and invent multiplication and stuff like this. It's like the central thoroughfares of math. And I have another question to you, because you started saying some very interesting things here about the time, and forward and backward in time and space, physics things, right? So I'm curious.
This is everyday time experience.
Right. So my question to you is this. First, I would like to understand how strongly are you arguing that are you making a physics claim that the physical world has some non-mathematical properties? And if you do believe that the physical world has some non-mathematical properties, I'd love to hear a bit more about what you think those non-mathematical properties are.
Okay. Well, I mean, I guess we go back to the original question, right? So, for example, if you ask me, okay, if you take future, past, and present, and you take those for granted, let's say present defines what future and past is, and the present is constantly changing, then therefore, the question is, what is now? And then in the way we use it in language, you could say, now that we're all in this room, or we could say, now we're in the mid-November, or now that the elections have just passed, or now that we're approaching the end of the year, or now that we're at the beginning of the millennium. All those nows have different extension. Some nows are very precise, like right this second I'm answering your question, right? But the now could also be that we've been here for 45 minutes or whatever it is. So then the physical definition of now doesn't exist, because you have to adopt a mathematical system to map it on this notion. So then you would say, okay, now is going to be a number in the real line that you're going to call 0, and then you call this plus or minus or whatever. Yes, but why the real numbers? I could have picked the hyperreal numbers, which include non-Archimedean numbers that don't follow all the axioms of the real numbers. So Archimedean numbers, by the way, are numbers that are so small that are smaller than any real number. So it means, like, let's say you take, for example, 1/10, which is small. But if you multiply by 10, the result is 1. Okay, pick a smaller, 1,000, 1 over 1,000. You multiply by 1,000, you take 1. 1/millionth, you multiply by million, the result is 1. Well, a non-Archimedean number is so small that no matter what number you pick to a real number you multiply with, you never reach 1. So that's how small it is.
Yeah. So
Again, imagined. It's an imagined, very
right.
specific.
But I wonder if you
So,
would you say that you disagree?
how long is now,
But
physically?
But would you say that you disagree with Einstein here about
Oh.
when he said that the time is just
I
the
don't
passage of
disagree.
time is just a stubbornly persistent illusion?
No,
You know,
I'm not.
when he said that rather than thinking of the true reality as being the stage where things happen over time, we should think of time as the fourth
So-
dimension.
I'm not in the business of dealing with saying he's right or wrong. That's not my study. What I've studied is what are the notions of present, future, and now.
Because I thought you were saying that this is something non-mathematical about nature, the idea of a now.
Yeah, the now.
Are you distinguishing between an imprecision in the language, an imprecision in the concept, an imprecision in the cultural notion versus a reality, either physical,
But tell me in
or-
physics, how long is now?
platonic?
How long is now in physics?
We don't really have it now that much.
Exactly.
Well,
That's
We
my
have-
point.
We have a beat of instance in the continuum, or there's other ways of looking
Exactly.
at it.
So, but now
but-
exists as a very precise notion, even though it has many meanings, but they all have one property, all
But
these
are you
meanings.
saying that this is an instance of something that's non-mathematical? Because there's a difference between saying, I have a mathematical notion of a precise moment in time, I can't
Yes, because
realize
I want
it
to
in
give you,
physical reality.
I want to give you an example.
But I can't realize it in physical existence, but that doesn't mean that that's a demonstration of a non-mathematical phenomenon.
Okay, so
Would that be
what I
fair,
give you
Max,
an
what you're
example
saying?
is if we take present, future, and now as basic blocks, okay, and then you mathematize that in some way. We leave the question open of how long now is going to be, but let's just leave it there. At least we know one thing, is that now is going to be between future and past, let's say. That's one property. Well, it turns out when you study other cultures, it's not always the case that you would have these three categories. So, for example, for the Aymara of the Andes, which I've spent some time studying.
What bugs me is, doesn't that
But wait.
fact tell us something about other cultures rather than tell something
No,
about the
because
universe?
this is going to be a different understanding of temporal experience. But I think the main difference here is that I'm studying the sense-making of experience and how we create abstraction to make sense of the experience. You guys are assuming that the numbers and the physical things are already existing. Some of them do, like planets and so on. But that the numbers that go in the system and the equations are pre-existing.
Maybe I
And
can
that's a
say
big
this another way.
Can I finish the
more-
Aymara example?
Sure, please.
Okay, so the one thing I was studying there is that for them, past is not behind them, is in front of them, and future is behind them. So they use the different properties of the body for characterizing that. And there's one interesting entailment is that there's no distinction between present and past. Because there's two categories only, the known and visible times and the unknown. And that you can see not only in grammatical markers and linguistic and lexicographical material, but also in gesture production in real time. So it means we could adopt, let's say, the axioms of the real numbers, and least, for example, the least upper bound to say that the now is the most recent known time, but is not separate from the past in the way we separate it. So the question, coming back to your initial question, is what is the mathematical structure of that in which you only have two categories, not three? And, it's clearly a different mathematics.
So
it's not the same.
Actually, we're really, really at the boundary of now.
Whoa!
Like really at the boundary
Now
of
that
now.
we're ending.
Yeah. I do want to say that I think what's so fascinating, I can't tell you how many slides I have, people.
Oh, that's
We'll-
right.
we'll
You had like
have to-
20.
No, I mean, I told you my slides don't matter. This
It's a mathematical
matters.
number, though.
Yes, it is a finite
Very
mathematical
specific.
number that may or may not exist in reality. But this is the exciting part, and what I really feel, there's so much I wanted to talk to you about where math occurs in the brain and how interesting that is. Of course, we identify where language occurs in the brain. Why shouldn't we be able to identify where math occurs in the brain? There's so much I want to talk to you, Max, about the multiverse, but we are a full hour in, and I love this, and I think we're going to have a part 2. Maybe not live. Maybe we can do a part 2.
What about that?
Part 2.
Part 2?
Max and Rafael.
That's a number.
I'm at
2.
2. Do we all agree on what number that is?
Smaller than 1?
I'm
or
going to
bigger
get you
than
two in a studio, and we're going to do this as like a radio thing. We're going to do this for sure for Pioneer X Broadcast. Before we open this up for questions, please join me in thanking my very invigorated guests.
Thank you.
That was a lot of fun.
Thank you. That's a lot of fun, yeah.
So thank you for the talks. It was lovely listening to y'all. I guess the problem I have is like the sense or the term discovery, because I'm like, are you discovering or are you just observing something and then relaying it in an invented way? Because I feel like discovery isn't in a lot of languages because things already exist before you even observe them. You didn't discover it, it's there.
That's a good question. I think to maybe clarify that, in the book that I'm finishing up now, or I should be finishing by the end of the year, I give an example precisely to clarify that question. So, which is non-mathematical, but it would apply to mathematics, or at least that's the way I see it. So, let's say you take an athletic event like high jump. That was invented, centuries ago, and the Greeks used it in the Olympics, and it's still with us today. Well, at the beginning, the rules were clear. You just go over a bar, and you have to jump over the bar. And then people started going over like ventrally, kind of going like this. But one guy, Flosbury in Mexico, 68, he discovered that actually it wasn't a very good technique to jump with the 2 legs or to go ventrally, but to go heads first. And that was the first guy ever, and he actually discovered that. He said that I discovered that it's a better way for doing it because of gravity and momentum and et cetera, and it just went over, and now that's every single athlete would do it that way.
I'm still doubting.
The Flosbury flop.
Yeah, I'm still doubting that he discovered it. It was in him. He could do that.
Yeah.
He practiced it. He did different variations.
Or the fact of it.
Like one of them worked, he observed it, and it was like, I can repeat this.
Yeah. So
And it wasn't discovered. It was, he could do that.
Yeah, maybe another way we could answer your excellent question here is if you could just compare the word invent with the word discover. When you're talking about invent, there's something that did not exist, and then you came up with it, and now it exists. Whereas if it's something that discovered, that means it did exist even beforehand, but it wasn't in your head, you didn't know about it. And now you become aware of it. To me, that's what a discovery is, whether it's Neptune or a new way of jumping higher or the dodecahedron.
Maybe you would like the distinction invented versus uncovered. It's suggesting that it might be new to you, but it was out in the world. In fact, what you're saying is even more Platonist in a way, saying it always was, and you've just come to know it in a way. We've got a Platonist in our midst.
Thank
Yes,
you.
somebody who has an answer
Thank you.
to the question.
Thank you.
Thank you so much. Next.
Yeah, great conversation. I want to know, mathematics can really be boiled down to logic. So is logic invented or discovered? Do you actually, when you create a logical argument, don't you discover something?
So you're talking about formal logic, symbolic logic?
Logic. So any kind of logical argument that you make.
Yes. Well, again, we have different logics. There are different levels of logic, some with quantifiers, some quantifiers over...
But those are just symbols, right?
No.
I think you mean even in a conversation,
Right.
reasonable, reasoned.
Yeah, right.
Thesis
You can
and
prove
argument.
something is true or not.
Yeah,
Right?
so that's a great example actually. So for Boolean logic, the simplest kind without the quantifiers, is an example of a mathematical structure which you can study, and it's called Boolean algebra. And then there's lower predicate calculus when you add this existence predicate and so on, and that's another different mathematical structure. So mathematicians now rather than talking about the logic, they study many different kinds of structures,
Exactly.
including all the different versions of logic
Right.
as well. There.
So a proof that something is true is really an exercise in logic, and you're actually discovering something.
There were fundamental principles like, for example, modus ponens, right? Which already the Greeks were studying, like saying, A implies B, and then you say A, therefore B. And that's a valid argument, but as long as the premises are true. If the premises are not true, then it's a valid argument, but it's not a sound argument, and they make differences of that sort. So as long as you keep it very simple, it's still doable in the oral language. But when you get into symbolic logic, you need writing, and writing is a human invention that existed 6,000 years ago, and symbolic notation is only after about Boole, and that's it. So then you get all these complicated formulas that require now writing notation, and then we're in a different realm.
And mathematics has been like New York. It's kind of expanded its domain over time. In the beginning, mathematics was all just about numbers and simple geometry, and now gradually it's absorbed more and more things, including logic. Most mathematicians would just view logic as just part of math.
Actually, Bertrand Russell was one of the persons who said, math is just that thing, but we can reduce everything to logic, and the job is really to find out logic, but that thing fell down when, Gödel's incompleteness theorems came in 1931.
Thank you so much for your question.
That was such a good segue, because I was just going to ask about your thoughts on Gödel's incompleteness theorems and whether you thought that...
Not that we planned this, right?
I guess I was wondering whether you think that there's an element to math in our understanding of the world that's fundamentally unknowable or contradictory, or if we just can't figure it out.
Right. Well, that was a very important principle in European science in the late of the 19th century. The ignorabimus, so like there are certain things we will never know, and there was some physiologists who were very well known for that, saying there's a lot of stuff in physiology, not math, that we will never know, because that's how science works. But there are other people like David Hilbert, great mathematician in the late of the 19th century, early 20th century, who believed that was not the case. Math is something where you can always know and decide whether any statement in any axiomatic system would be true or false.
Gödel prove that Hilbert was wrong?
Exactly. Well, he was wrong on that part. He wasn't wrong in everything, but at least in that statement.
That would be quite a proof.
Yeah,
Everything
exactly.
Hilbert ever said was wrong.
Gödel incompleteness theorems address arithmetic with addition and multiplication. If you just take arithmetic and addition only, without multiplication, the system is complete, and every statement in that domain is decidable with the axiomatic system. So the interesting thing about Gödel's work is that he just put multiplication in it. And then all of a sudden the system with this particular axiomatic system would be, in this particular case, would be Peano axioms, would be undecidable. So it would always be the case that within that axiomatic system there will be at least a statement that you would not be able to decide, and that's kind of the
I
outcome
want to
of it.
let Max reply, but I feel I owe it to my audience to say something about what everyone's talking about with Gödel's incompleteness theorem. The idea was Gödel did the mathematical equivalent of writing down a mathematical statement that amounted to the statement that this statement is unprovable. It was a mathematical relationship that was true manifestly, but could not be proven as a theorem starting from the axioms that Rafael has been talking about, could not be proven in the context of that axiomatic system. And he also went on to show that there are an infinite number of numbers about which we can prove nothing. So there are an infinite number of numbers about which we will never know anything. There's infinite true facts about those numbers, but they're not accessible to us as theorems yielded from an axiomatic system.
Right.
Max, please.
So on one hand, this is all really fascinating, and on the other hand, our universe doesn't really care so much, I think, because Hilbert had this pipe dream that wouldn't it be nice if you could use mathematics, in particular number theory, to prove its own consistency. And Gödel was like, sorry, it's impossible. But in hindsight, this was sort of a misguided hope, because if you ask some guy, are you honest? And the guy says yes, you haven't learned anything, right? If he's honest, he'll say yes. If he's dishonest, he'll probably also say yes. And the same thing holds in math. If you start with something which is inconsistent or false, from that you can derive anything, including the proof that it's true, right? So if it had succeeded, it wouldn't really mean anything anyway. Gödel showed that you couldn't do it. The one thing that might have been nifty would be if you could use some even simpler math than the thing you're trying to prove the consistency of to prove the consistency. But Gödel put the kibosh on that also. If you can't even use the full strength number theory to do it, obviously you can't do it with something lesser. I think our universe really doesn't care, in the sense that all of this stuff that you're trying to prove is, can you prove things? Those are things you do with the language of mathematics, so-called formal systems that are describing the mathematical structures that we see on the screen that we're trying to talk about. What I was arguing is that our universe isn't a language, it's a mathematical structure. It has some properties. And then, so what if there's some things about it we humans aren't able to prove? That's our problem. That doesn't mean our universe is inconsistent. And finally, it's interesting to remember that the whole crux of what Gödel did requires the infinite. And if there isn't anything actually infinite in our universe, then there's absolutely nothing to worry about.
But you could say that Gödel proved, unlike currently in physics so far, that there is no such thing as a mathematical theory of everything. Yes. And that's very profound, I think, with physicists pursuing a mathematical theory of the laws of physics.
And he proved that even just for something as simple and knowable and tractable as arithmetic.
I mean arithmetic, sorry, yes. So it was an A word. Yes, arithmetic, absolutely. Please, next question.
Fascinating discussion, something I've been struggling with for a long time, and I don't feel any clearer than an hour ago, but I have two I have two questions, probably one for each of you. So if math is just invented, and there's, say, a world that there's no humans, would you still be able to, would some alien civilization be able to count things like, is a planet here and a planet here, and these two planets come into orbit around each other, is there now more than one planet? Is that something that would just exist in the world? Or it seems like you're saying no. My question for you, Max, is that...
I'll let you answer that first.
Okay.
Well...
that's what I don't quite get. No, or even forget about counting things. Forget about things being objects.
So the way I take that question is that in order for the organism you're describing, you called it extraterrestrial, but it would have to be a sentient being. So a being that would have some kind of ability to perceive something. Heat, brightness, texture, quantity.
But so you're saying nothing can exist in the world without being observed?
No, I'm not. I don't talk about whether things exist in the world or not. I'm talking about whether mathematical objects exist as planets and species. That's the whole. That's what we invent, like English grammar. I'm not saying whether it exists or not in the universe. Is invented, and it's not invented by one person or 15 or 20. It's a societal thing and a historical process that comes out. Mathematics, as we practice it, requires writing. There's no mathematics that goes beyond basic things that does not have writing of some sort. And that goes back to because the human brain and the human nervous system only provides very basic capacity for working memory. We can only hold very tiny little information at once. So we need to make marks and things externally. So if your being has a certain type of nervous system, a sort of a type of societal organization and so on, and a certain moment in history, then certain regularities will be discovered and sensed, and then some conceptual system will come up to grasp those regularities.
So I would answer this question differently with a yes, because the central assumption I start with in my book, Our Mathematical Universe, is what I call the external reality hypothesis. The hypothesis that there is an external reality out there independent of us humans, that Neptune would exist just fine if there were no humans. The Andromeda Galaxy would exist just as much if we weren't here. And ultimately, the job of physics is to try to figure out how that external reality is without involving any sort of human cultures or terminology and stuff like that. And I then make this argument in the book, which sounds very surprising, that if you buy into the external reality hypothesis, it leads you inexorably to the conclusion that this external reality is in fact a mathematical structure that we live in. So I say that this mathematical structure exists not only in a mathematical sense, but it's the one we live in. So it exists just as much as anything else does.
So Max, to respond a little bit and extend this excellent question with what Rafael was saying, do you think human beings need to be here to discover the quark, for the quark to be a mathematical object?
No.
Do we need our scratches and our scrawlings? And
So what humans? Which humans? When?
it doesn't matter. Conscious beings. Do we need minds for the quark to be a mathematical
No,
object?
I think that the quarks and everything else, they have the properties that they have, regardless of whether anyone observes them or not.
Sorry, just the second half of my question is, I want to believe what you're saying, and I think I do, but why are there any regularities then? Why is there any order at all, assuming that we're not living in somebody else's simulation?
That's a
like, why is there any
That's a
pattern at
fantastic
all?
question.
If it's out there already, and
Yeah.
we didn't invent this, why is it out there?
That's a
what-
fantastic question. Mathematical structures generally have properties which you might call regularities. That what ultimately defines them is it's a bunch of abstract elements with relations between them, properties. However, your question is very good, because clearly you can write down some mathematical structures that are just such a total mess that if there were anyone in there, they couldn't make heads or tails of it, right? It would seem like. And I'm pretty confident that in those mathematical structures, there's no psychon, because if there's anyone there, they wouldn't even have any evolutionary reason to invent the brain, right? If everything just looked completely random. You should only expect intelligent life to evolve in a place where it's useful to try to take in data from the environment and predict things about the future. And it's only useful if there are regularities there that you can discover and make use of. So most of those icky, super messy structures are just stillborn. There's nobody home there to appreciate them.
Okay, I think you convinced me.
Thank you.
Thank you. And this is our last question. Come friend with the Rubik's Cube.
I believe that to invent anything as a theoretical object, you're going to end up making discoveries about what you have invented, and in order to discover something, you need to invent notation to do it. They are interlinked, and so to answer the question, is math invented or discovered, as an either-or statement, is kind of necessarily contradicting yourself.
Okay,
So-
we're done. Thank you very much.
Can I just add to that you also, by bringing up Rubik's Cube here, beautifully illustrated your own argument, because it was invented by the Hungarian Rubik, and then, after he had invented it, people studied the invention and discovered all these remarkable properties. There is an area of mathematics called group theory.
That's right.
And you can study the group of all possible things you can do with the cube, and people have studied it at great length. That's how we ultimately know how many different ways the cube can be arranged, and what the fewest number of moves you need to make to go from any to anything else, etc. So I don't only agree with your point, but I thought you brought the perfect prop to illustrate it.
Yeah. No, and also it shows, the cube, the material cube is a, human invention, and then you look at the properties. But yeah, you're right. There's probably, I wouldn't call it a contradiction, but it's maybe the fact that the question is reduced to one or the other as being mutually exclusive. And in this case, as you said, you can invent something and then you discover things after, let's say, having other things invented like writing, and then all of a sudden you discover new things. And so it goes with the saga of human condition. Yes.
One of our friends and supporters here from the Simons Foundation, Jim Simons, famous mathematician, when asked, is math invented or discovered, he said yes.
There you go.
I think that's a good.
Okay, good.
conversion.
Sorry to steal the last nine. Thank you.
Thanks. Thank you.